Okay, thank you so much, Ben, for the nice introduction. And yeah, let's get started with this presentation. Today, I'll be sharing the findings of a project we had on load rating damaged double T girders for South Dakota local roads. First, let me thank my graduate student, Sandeep Rimal, and my colleague, Dr. Webby, who was the co-PI of the project, and thank Dr. So, who was the co-PI and helped us with the field testing as well. And I would like to also thank the, the sponsors of the project, South Dakota Department of Transportation and US DOT through Mountain Plain Consortium in NDSU and multiple industry basic collaborators that basically helped us through the project. I want to give you a quick background why we did this study. The most common type of bridge on South Dakota local roads, not the highways, is double T. They are pre-stressed, pre-tension, open channel girders, kind of inverted U shape. And there are more than 700 of those in service in South Dakota. And 75% of those are at least 20 years at this time. And we have found that the structural detailing, especially the longitudinal joint, are structurally deficient and also aging environmental condition. We are at cold region, so de-icing and freeze and thaw basically always makes an issue there. We have found a combination of all of those and also flooding will deteriorate the performance of the structure and will cause damage. We can see two cases here in this slide. And the question is how you can incorporate these damages in your design or in your analysis to make sure that these bridges are safe to public. One way to answer that is through the load rating. AASHTO allows three different ways. The allowable stress all the way through the load and resistance factor rating. We are using FR technique in this study. And if you take a look at that equation, you will see that it has three components. Dead load component, we usually don't touch it, it is what it is, and live load component and capacity component. We did not find any study that would relate the element level damage to these load rating parameters. However, AASHTO will tell you in general, if you're not happy with the condition of the bridge, you may overall reduce the capacity by 0.5 or 0.15%, depends on the condition that you assign to bridge. So it's overall not for the element level assessment. And then we wanted to do it at the element level and see how load rating parameters would change. To answer that, we completed all of these bullets. We first found that we need to change a bit the definition of damage and damage types for double T's, and we reviewed multiple inspection reports and DOT database. We performed field testing of two bridges. We strength tested two 45 years old double T girders. We performed more than 1,000 analysis, and we ended up with a load rating methodology that you might use to incorporate all of these damages in your load rating process. So I'll give you a quick overview of what was done for some of those important bullets I showed earlier. Let's get started with the damage categorization. AASHTO has a long list of damage types and condition state for different elements. However, we have found that they are more qualitative, and specifically for double T, we needed more quantitative definition. So if two inspectors go to the same site, they would report the same kind of damage and damage state, not two different things or three different things. So we ended up with this updated definition, but we divided that for stem and flange. You are seeing the stem on the slide. For example, if your cover deteriorates and you're at damage state 4, this is what we mean of that. And we provided different images and illustrations for the inspectors to quickly identify the right box in the cell or the right cell in this table. And we did the same thing for the flange of double T as well. We tried to be comprehensive, include everything, and to have basically definition that would be easily understood and determined by different inspectors. So same thing here for the flange of double T. So based on that new definition that we had, which was in line with AASHTO four-level damage state, we went and basically reviewed more than 375 inspection reports and STDOT documents, and we found that the most common damage for stem of double T is cover deterioration and cracking. It's not surprising, but we wanted to have that information documented. And we also did it for the flange. We have found that the common damages are cracking, cover deterioration, and the cracking or the damage of girder-to-girder longitudinal joints. The last one is super important, because if your joints of the girders, adjacent girders, are not performing as you want, then the live load transfer between the girders are not those that you assume. So we need to take care of that or see how this damage will change the load rating equation. So answer all of these, we started the study with field testing, and we wanted to better understand live load distribution of damaged double T girders, especially those with the bad longitudinal joint. So we inspected 10 bridges. We tested picked two of those for testing. So one was 34 years old, and the other one 38 in Lincoln and Moody County, 42 feet long to 50 feet. And the reason that we picked these two bridges, the review of inspection reports showed that most common bridges in South Dakota, local ones, are single span, 40 to 60 feet long, and they are non-skewed. So we picked these two based on that definition. And the other reason was the longitudinal joint. We picked the two bridges that had the worst longitudinal joints. Here is a bottom view, underneath view of the bridge, and you can see a sign of corrosion there and change in color. Also at the side of the girder, you can see the stains coming from the water leaking from the joints and some other damages. So unfortunately, we could not find any bridge, at least in the database, that had damage state 4 for the longitudinal joints, but these two that we tested had damage state of 3. We followed AASHTO, perform a typical load rating, follow typical protocols. We perform static testing, dynamic testing. We initially started dynamic with 55 miles per hour because it was local road, gravel load. We were concerned about safety of the crew. We changed dynamic load speed to 35. We use a 3-axle dump truck, and the total weight of the truck was 50, and we measured the axle weights at the STDOT facility. So we tried to use a common load pass, basically in a way that each girder will be tested at least once, and we actually repeated each pass twice because the size and the span lengths and the widths of the bridges were not the same. So the load pattern is slightly different, but the whole purpose was to engage every single girder at least twice. And here is a summary of this of the findings from the load rating. On the y-axis, you can see the flexural girder distribution factor, and the x-axis is the girder number from 1 to 8, and you can see girder 1 to 8 in the slide too. And we found that even though the damage of the longitudinal joints were around 3, the AASHTO equation, this dashed line, is sufficient to estimate the live load distribution. We also did it for the shear, but the shear demand was so low that I excluded that from this presentation. So it was not governing load for the analysis. I talked about that. Let's move on to the dynamic load allowance. We also found that for these two double T bridges with condition state 3 in longitudinal joint, the AASHTO equation is safe because these guys gave us probably less than 10%. However, the AASHTO requires 33% amplification factor. So you can go ahead and safely use AASHTO. So based on these testing, we came up with kind of a set of recommendation for updating the live load. If you're at damage state 3, follow AASHTO. However, if you're at damage state 4, that's where I'm assuming that the joint is completely lost. The two girders are sitting side by side. They don't talk to each other. So you need to treat them as individual girder. So with that, I came up with this text, or we came up with the text at damage state 4. Your girder distribution factor is the greatest of factor you're getting from exterior girder, from interior girder, and 0.6. That 0.6 was assume that there is no connection. Each girder will take half of the weight of the truck, the transverse direction, add 10% to it, so 0.6, just to stay on the safe side of the analysis. So at damage state 4, use this line of equation to calculate your girder distribution factor for moment and shear. And for dynamic load allowance, the AASHTO provides enough safety factor, so just use that. And we also did strength testing of 245 years old salvaged girders. We went to Rapid City, we picked 2 girders, and they actually basically extracted those 2 girders and shipped us for testing. So the one was 50 feet long, another one was around 30. The goal was to test 2 different lengths, hoping that at least the shorter one will fail in shear, so we can get a sense of the shear capacity as well. And here is a video. I hope that Zoom shows the video for you. That's the strength testing of the 50 feet long girder. Was brittle, it was bad. We lost a few sensors, but that absolutely worth it. Here's a slow motion version of the same girder. This damage that you see, it was as received. So that was what was basically on site, and we saw it here. So the flange of the girder failed, and the failure was brittle. I guess it paused for some reason. Okay, you can see how bad it was. My student reaction back there. So brittle failure, not the one that we want. Here's a forced deformation behavior. The gray dashed line here's AASHTO limited state, service 1, and the strength. Yeah, the girder didn't even meet the service limited state, let alone the strength limited state. So it was bad. We used this information to develop a moment curvature curve, or general method that basically using moment curvature to be able to estimate the capacity of a girder damaged like this and many other scenarios. We also borrowed 4 test results from the literature. We updated our modeling method and developed modeling method, usually moment curvature, and using AASHTO shear equation to be able to estimate the failure mode of bridges with damages. And here is a kind of a summary of our proposed load rating technique. I discussed this. The load rating equation has 3 components. Dead load, we don't touch it. It is what it is. Live load and capacity. I briefly talked about live load and provided recommendation. We discussed about that quickly. And that's done whenever there is a bridge and you have a damage at different points, specifically in the longitudinal joint, you need to update your live load based on the recommendation. And the challenging part was the capacity, how you will take care of capacity. We came up with a short version of AASHTO, a slightly modified equation. So you start with undamaged condition or capacity of girder, follow AASHTO or another document to calculate the moment shear capacity of your girder, undamaged one. And then we will provide you a reduction factor to adjust your undamaged capacities and basically accounting for different types of damage that you might see. So to give you that phi C or condition factors, we did more than 1,500 analysis and tabulated this factor for different types of girders we had in the state and different scenarios of loading. It's kind of the summary of that. Whenever you see a damage in the stem of the cover with condition 4, you need to reduce your moment. Moment does not change there, but you need to reduce your shear capacity 25%. And if you see any other damage is there, you go and subsequently change either shear moment capacity based on that damage. To calculate these condition factors, we follow different scenarios. Let's talk about the stem cover deterioration. We assume that damage state 1, there is no damage, so that's your undamaged capacity. At damage state 2, you're going to lose 1/3 of the cover, either from outside, inside, or bottom face. Do a moment curvature analysis, follow AASHTO equation for shear, find the worst case scenario and report that as your phi C for condition state 2 of cover of stem. Do the same thing for condition state 3, remove 2/3 of the concrete cover, and then perform the analysis and report the worst case scenario as the condition factor for that. So we did that for multiple different damages and multiple different scenarios. We tried to stay on the safe side. Here's one example how we did it for the cover of the flange. This is undamaged. You can do moment curvature, and then you remove, let's say, 2/3 of the cover or whatever it was in the definition, and then you analyze this new section using moment curvature analysis. The ratio of the two moments are your phi for the moment of this damage at this damage state that you see on the screen, and we rounded these guys. We provided a nice table for every single section that is has been used in South Dakota. And now if you are a bridge engineer, you see a damage, you go to this table, you extract your phi, and you adjust your shear and bending moment factors in your calculation. So now you know how to adjust the live load, you know how to adjust your capacity, you can go through the load rating following AASHTO, and then have an updated version of load rating, including all of these damages. I'll stop here and maybe we can answer a few questions.
Yeah, great. Thanks for the presentation. We are on time. We've got a few minutes, so if folks have questions, feel free to put them in the Q&A. I had a couple questions, or I'll ask one, Mostafa. For your load distribution recommendations, you ended on a 0.6 because it was slightly higher than half. Was that for a specific geometry of double T, or did it apply to all, or how was it kind of narrowed in on?
Perfect question. Yeah, all of double T that has been used in South Dakota are around 40 to 42 inches wide. So that would fit nicely to 6 feet axle spacing. So there's no way that you can have both axles at the same time on one girder, unless that's the middle one and you have two trucks passing at the same time. Yeah, so that half was based on that geometry that's kind of set here.
Okay, great, thanks. We did have one more question in the chat. Have you suggested any retrofit options and or cost benefit ratio for these options?
That's a perfect question. Yes, we did. Not part of this study, another study, how to fix that longitudinal joints. We ended up with a new kind of connection, removing the bad concrete and having a keyway of UHPC with pockets every 2 or 5 feet, I guess. And then we perform full scale testing of the rehabilitated bridge in our lab performance. So yes, the rehabilitation, at least for the longitudinal joint, are done, but we haven't done anything for the stems or basically any other type of damage.
We'll have one last question here. Are the results due to the design of a double T bridge, or can the data be applied to bridges outside of South Dakota?
As long as your geometry fits, yes, you can use this table. Otherwise, you may need to make your own table and follow the methodology. So the methodology is applicable not only to double T, to any bridge, but you might need to make this table.
All right, perfect. Thank you.